So shielding happens when you have more than one electron in an atom. And the reason that it's happening is because you're actually canceling out some of that positive charge from the nucleus, or that attractive force, with a repulsive force between two electrons. So if you have some charge in the nucleus, but you also have repulsion with another electron, the net attractive charge that a given electron is going to feel is actually less than that total charge in the nucleus. And shielding is a little bit of a misnomer, because it's not actually that the electron's blocking the charge from another electron. It's more like you're canceling out a positive attractive force with a negative repulsive force. But shielding is a good way to think about it, and actually that's what we'll use in this class to sort of visualize what's happening when we have many electrons in an atom and they're shielding each other. Shielding is the term that's used. It brings up a certain image in our mind, and even though that's not precisely what's going on, it's a very good way to visualize what we're trying to think about here. So let's take two cases of shielding if we're talking about, for example, the helium, a helium nucleus or a helium atom. So what is the charge on a helium nucleus? What is Z? Yep, so it's +2. So the charge is actually just equal to Z. We can write +2, or we can write +2e. E just means the absolute value of the charge on an electron. When we plug it into equations, we just use the number. The E is assumed there. So let's think of what we could have if we have two electrons in a helium atom that are shielded in two extreme ways. So in the first extreme way, let's consider that our first electron is at some distance very far away from the nucleus. We'll call this electron 1. And our second electron is, in fact, much, much closer to the nucleus. And let's think of the idea of shielding in more of the classical sense, where we're actually blocking some of that positive charge. So if we have total and complete shielding, where this can actually negate a full positive charge, because remember, our nucleus is +2, one of the electrons is -1. So if it totally blocks it, all we would have left from the nucleus is an effective charge of +1. So in our first case, our first extreme case would be that the Z effective that is felt by electron number 1 is going to be +1. So what we can do is figure out what we would expect the binding energy of that electron to be in the case of this total shielding. And remember, again, the binding energy physically is the negative of the ionization energy, and that's actually how you can experimentally check to see if this is actually correct. And that's going to be equal to negative Z effective squared times RH over n squared. So let's plug in these values and see what we would expect to see for the energy. So it would be -1 squared times RH all over 1 squared. Since our Z effective we're saying is 1, and n is also equal to 1 because we're in the ground state here. So we're talking about a 1s orbital. So if we have a look at what the answer would be, this looks very familiar. We would expect our binding energy to be -2.18 times 10 to the -18 joules. This is actually what the binding energy is for a hydrogen atom. And in fact, that makes sense because in our extreme case where we have total shielding by the second electron of the electron of interest, it's essentially seeing the same nuclear force that an electron in a hydrogen atom would see. All right, let's consider now the second extreme case, or extreme case B for a helium atom. Again, we have the charge of the nucleus on +2, but let's say this time the electron now is going to be very, very close to the nucleus. And let's say our second electron now is really far away, such that it's actually not going to shield any of the nuclear charge at all from that first electron. So what we end up saying is that the Z effective, or the effective charge that that first electron feels, is now going to be +2. Again, we can just plug this into our equation. So if we write in our numbers now saying that Z effective is equal to 2, we find that we get -2 squared RH, all divided again by 1 squared. We're still talking about a 1s orbital here. And if we do that calculation, what we find out is that the binding energy in this case where we have no shielding is -8.72 times 10 to the -18 joules. So let's compare what we've just seen as our two extremes. So in extreme case A, we saw that Z effective was 1. This is what we call total shielding. The electron completely canceled out its equivalent of charge from the nucleus, such that we only saw a Z effective of 1. In extreme case B, we had a Z effective of 2, so essentially what we had was no shielding at all. We said that that second electron was so far out of the picture that it had absolutely no effect on what the charge was felt by that first electron. So we can actually think about, now we know the extreme cases, but what is the reality? And the reality is, if we think about the ionization energy and we measure it experimentally, we find that it's 3.94 times 10 to the negative 18 joules. And what you can see is that falls right in the middle between the two ionization energies that we would expect for the extreme cases. And this is absolutely confirming that what is happening is what we would expect to happen, because we would expect the case of reality is that, in fact, some shielding is going on, but it's not going to be total shielding, but at the same time, it's not going to be no shielding at all.